Hi, here's a quick video that will enable you to finish the next assignment in the counting chapter. So how many 8-letter words can be made by rearranging all 8 letters of pralines? Okay, so we were taught last time to make blanks, 1, 2, 3, 4, 5, 6, 7, 8, in order to calculate permutations. So for the first letter in the rearrangement, there are 8 choices. And once you choose, let's say N, let's say we want N to be our first letter, there'd only be 7 choices remaining. Say we wanted that to be I. And then from there on out, it descends. So this is clearly the same as 8 factorial based on what we learned before. And we also could have used the NPR formula we saw before, which is n factorial over n minus r factorial. In this case, that would be 8 factorial over, okay, this would be 8 total letters, and we're supposed to permute, meaning rearrange all 8 of them. So this would be 8 over 8 minus 8 factorial. So then that's 8 factorial over 0 factorial. Turns out that's the same as 8 factorial because strangely enough, 8 factorial is whatever, some big number, but 0 factorial is actually 1. And you can check that in your calculator to make sure it calculates right. All right, reminder of 8 factorial, where you can find factorial. It's under Math, Probability menu, option 4. Great. It's 40,320. If I try to divide that by 0 factorial, you'll find that 0 factorial is indeed 1 and not 0. Great. So this is 40,320 ways to make 8-letter words out of pralines. Let's try it again with banana. So let's say I choose A as my first letter. There was 6 choices there. And then let's say I choose another A as my second letter. Out of those were 5 choices left. Okay, so I use an A and an A. Okay. If I do the 6, 5, 4, 3, 2, 1 thing, that's going to mean that AA, let's say NB, NA, that would mean that that's the same, or that would mean that that's a different word than AA, NB, NA. Did you not see what I did? I rearranged these 2 N's. You didn't notice? Well, that's because those N's were indistinguishable. So there's a slightly different calculation you need to do if any of the objects you're arranging are indistinguishable. So we've got the N's that are indistinguishable from each other, and we've got 3 A's that are indistinguishable from each other. And so what we do is we do the same thing we're used to. We do the fundamental counting principle. We calculate 6 factorial. So I'll start by doing that. 6 factorial is 720. But then we also have to divide out all these parts that we don't want to count as 2 separate ones. So I don't want to count 2 separate N's as distinguishable. Like I don't want to say banana is different than if I move that, and oh, now it's banana. Like those are the same. So what you divide by is however many repeats there are, factorial. Divide by 2 factorial, and there's 3 A's that are indistinguishable from each other. So I'm going to also divide by 3 factorial to get rid of all of those options. So it turns out 2 factorial is just 2 times 1, so that's dividing by 2. 3 factorial is 3 times 2 times 1, so that's 6. So I'm going to end up dividing 720 by 12. And when I do that, I'm left with 60 options. So it turns out there are actually only 60 ways to rearrange the word banana into distinct 6-letter words. The 720 would represent like, oh yeah, sure, look, I can tell you I rearranged the A's in order here, but it's like, no, you didn't. Like the A's all look the same. So it becomes a smaller number of options if there are some indistinguishable pieces. This is reiterating that in mathematical terms. And then why don't you try and see if you can do Mississippi based on the principle I just showed you. Pause the video. So there are 11 factorial options if every letter was distinguishable. Since they're not, kind of listing out what's there. I don't really need to include the 1 because there's one of them. But looking at the other ones, I want to make sure I divide out the options. I get rid of some options. So I don't need all the i's to be considered different. I don't need all the s's to consider different. And I don't need all the p's to be considered different. So I'm dividing out 4 factorial times 4 factorial times 2 factorial options, which it turns out is 1,152 options just in how to arrange those indistinguishable parts. So if I divide 11 factorial by that, it turns out to be 34,650. That is much fewer options than if I didn't notice that all those and i's and s's and p's are distinguishable. All right, you're doing a nice job with that. Last thing I want to show you is going to help you with problem 50 on your homework. This is actually problem 48 from the textbook. It's just sort of some interesting ways to do algebra using permutation notation. So we've got NP5. So again, I'll put the formula here for permutations again. When you see NPR, that's n factorial over n minus r factorial. So that represents like the total number of objects and the number of objects you have to arrange out of that total. Sometimes it's the same number, sometimes it's a lesser number, but definitely this number is never greater than n. Okay, so I don't know exactly how many total objects I have, but I'm trying to arrange 5 of them. So if I just follow my formula, it's n factorial over n minus 5 factorial times, or equals 7 times n factorial over n minus 4 factorial. That might look like it is not a solvable equation, but actually there's a nice little trick that'll get you there. So what does n factorial really mean? So let's say n was 9, for example. Then 9 factorial, so n factorial, would mean 9 times 8 times 7 times 6, and I'm just going to pause for a second. So this must mean 9, n is 9, times 8. How do you get 8 from 9? Well, you subtract 1. Times 7. How do you get 7 from 9? Well, I subtract 2. Times 6. How do you get 6 from 9? You subtract 3. Do you get the picture? So you just keep going until you're out of numbers, until you get down to just 1. So let's see what that can help us with here. So if we treat n factorial as n, 1 less than n, 2 less than n, 3 less than n. If you think about what happens after n minus 5, shoot, I'm messing up. 6, 7, blah, blah, blah. Look at the bottom. The bottom is supposed to be n minus 5 factorial. So that's n minus 5. Then 1 less than n minus 5 is n minus 6, times 1 less than that is n minus 7, times 1 less than that is n minus 8. You can tell for the rest of time, these are going to cancel. And all that's left is n minus 1, n minus 2, to n minus 4. The rest cancels. Something similar is going to happen on the right side. And we'll see when we expand it that n minus 4, n minus 5, n minus 6, n minus 7, all of that cancels out top and bottom. And all that's left is that original 7, and then the n minus 1, n minus 2, and n minus 3. At this point, you can also eliminate some things that happen on both sides. So we could divide both sides by n. See that go away. I mean, that's within our rules of equation simplification. As long as you divide by the same thing on both sides, it's fine. We could also divide by n minus 1 on both sides and watch that disappear. So it turns out we're going to watch all of these disappear except for the n minus 4. That doesn't have a partner on the other side, and the 7. So guess what? You just solved it. Add 4 to both sides. We solved for n. It's 11.